spent the last hour and a half creating a video for you guys that apparently had no sound. So we'll see if I record this video and if it ends up having sound, or if I get to start over again. So it's iffy. We'll find out. So climate change. We'll start where we little review from last time, and then move on to what we need to know. So first of all, remember we have a greenhouse effect that keeps us warm and living on the planet. I'm so glad you're making like dinner while I'm trying to make this video. Thank you. That's very
permission to make dinner. That's
quiet. Anyway, I totally forgot where I was going. Okay, so greenhouse effect happens because we have a few gases in the atmosphere that actually re-radiate heat energy. Nitrogen is not one of those. It's our major gas in the atmosphere. Don't forget 78%. 21% is oxygen, also blind to light and blind to heat. Doesn't really help us stay warm at all. Argon doesn't either. It's about 1%, less than 1%. So greenhouse gases make up about 1% of the atmosphere if you are including water vapor in that number. Most people do not when they do that. I don't know why, because water vapor is our strongest greenhouse gas. It's the reason why we have so much warming. Some people say 60% of the warming is caused by water vapor. Some people say 80 to 90%. I don't know what numbers. A lot. That's the answer. It's a lot. So our main reason why we stay warm is water vapor. Now our main driver of climate change is carbon dioxide, because if we increase carbon dioxide, it allows us to have more water vapor in the air, because it allows us to have more heat. So more heat allows more water vapor, means more warming. More warming allows us to have more carbon dioxide, or actually doesn't allow us to have more carbon dioxide, causes us to have carbon released into the air more frequently, and then we have the ability to have more water vapor. Okay, other review here. Where are we at? So our main gases: water vapor, carbon dioxide, methane, and nitrous oxide. So our carbon dioxide increases from burning stuff, burning fossil fuels, burning forests. Methane increases primarily due to agriculture, rice paddy farms, any time we dam something, cows farting and burping too much, literally changing the climate we live in. And remember, methane is 20 times better at re-radiating heat energy than carbon dioxide, but there's a lot less of it, so it's not the biggest driver of climate change. Yada. Nitrous oxide, remember, our main reason why we're increasing that in the atmosphere is due to inorganic fertilizers that we're putting on our fields. Other gases are HFCs, so hydrogen, fluoride, and carbon there. That's hydrofluorocarbons. Our CFCs that are chlorofluorocarbons, are hydrochlorofluorocarbons. Oh my gosh. Any kind of halon mixed with a carbon is pretty much going to be assumed to be one of those gases. It's either a greenhouse gas and also creating a hole in the ozone layer. Thanks for chewing extra loud. It's not distracting at all. Okay, my son's here, by the way. Where are we at? All those chlorofluoro, hydrofluorochloro, all those are pretty much majorly used in refrigerants. What are other? I forgot. Cleaners and fire retardants. All right, ozone is also a greenhouse gas. So the fact that we have a hole in the ozone down in Antarctica, it's actually causing a shift in our jet streams. Don't think you need to know that, but it's kind of interesting. And we're losing heat out Antarctica. Antarctica is actually taking on more ice right now than it is losing ice, because it's a little cooler in that region. Past fluctuation. We talked about past climate change is caused by changing of our tilt of the Earth, changing of our orbit, and changing of the wobble of the planet, causing sunlight to hit us differently. So that is going to either increase ice on the planet or decrease ice on the planet, and then also allow us to have natural changes of carbon increase. Now, those are not cause of our current climate change. We know that one of the main reasons is it takes like 150,000 years for the climate to go from a glacial period to an interglacial period. Currently, it's not a 150,000 year change. We're looking at like a period of 200 years where we're seeing a drastic rise in temperatures, a drastic rise in carbon dioxide emission. Now, really drastic in carbon dioxide emissions. Remember, 280 parts per million from the Industrial Revolution, and we are currently sitting at about 408 parts per million for carbon dioxide in the atmosphere. All right, so this is our graph here. The top one is concentrations of carbon dioxide. You can see that uptick where it's immensely higher than it has been in the last 400,000 years. And then you see that temperature increases with carbon. We talked about that last time. All right, sun. We didn't talk about this last time. The sun doesn't put out the same amount of energy all the time. We also know that's not the reason for the current warming as well. But let me talk about it really quickly so we know what that is. All right, so sunspot cycle, the sun gets sunspots on it. And what that looks like is these dark spots on the sun's surface. Now, there's nothing wrong with the sun. There's just less energy flowing there and at that one spot. So it actually gets a lot cooler there compared to the rest of the sun. Now, you can actually see these with special sun protective glasses. Anyway, doesn't matter. When we have a lot of sunspots, we have a lot of energy coming, or more energy coming out of the sun. When we have less sunspots, we actually have less energy coming to us from the sun, which seems counterintuitive, but that's definitely what we see. Now, the sunspot cycle, this graph here shows that sunspot cycle goes up and down, up and down. The high peaks are more sunspots, more output from the sun. Low peaks are less sunspots, less output. And so what we see is we see a peak, and then it will get a little bit less, and then we get a high peak, and then we get less. So right now, we're seeing this downdraft at about the year 2000. Now, like the last 15 of the hottest years on record ever have been since the year 2000. And the sunspot cycle we see here, it peaked at about 2001, and the sun's been putting out less and less energy ever since. Now, these cycles that I talked about before with the orbital change, the tilt change of the Earth, all those also are lined up to be in a cooling pattern for the Earth. So we see all these different cycles lined up, and they're all saying we should be cooling instead of warming. But we're not. We're warming. Now, when I said a lot of warming, we're getting a considerable amount of warming, we're actually talking about a half to a degree of Celsius. One is what we're talking about. Now, this is our global temperature. And we talk about global temperature, we're talking about global averages, the whole planet. So the equator, we're seeing almost no warming whatsoever. And as you go higher up in latitude on the planet, we're seeing considerable warming. So some places in the Arctic, we've actually seen more than 8 degrees of warming, which, that's in Fahrenheit. So more of like 5 degrees Celsius in warming. So we're seeing considerable warming in the Arctic. And what we're really noticing is patterns of, we're seeing less warming in the summer than we're seeing in the winter. Winter months are having a lot more warming. And so we're melting a lot of our snow or our ice pack. Now remember, feedback loops. Positive feedback loops go to amplify conditions. They make them more, whatever it is, until a new equilibrium is reached. So they don't keep going forever, but there might be the new normal. And the new normal may be a planet that we're having a hard time surviving on. Now, a negative feedback loop, if you recall, is something that reduces an effect. So let's say if global temperatures were going up, and that caused something to have more ice on the planet that would reduce global temperatures, then that would be a negative feedback loop. Most feedback loops, and when we talk about climate, tend to be a positive feedback loop that cause things to amplify and reset. An example of that would be raising global temperatures. Raising global temperature causes us to have permafrost melt. Permafrost, meaning permanently frozen ground, has a lot of organic material in it that's not decomposed. So when that stuff starts to warm up, it decomposes, it releases methane. Methane's a greenhouse gas, a pretty potent greenhouse gas, increases warming, and temperatures rise even higher, causing an increase of melting of that permafrost. So we get this situation where the feedback loop's causing more and more heat to happen until eventually we come to a new equilibrium. One of those things, or examples of a feedback loop here, is emphasized in the Arctic sea ice. Here, this image shows this yellow line of our average minimum ice cover. So how small the Arctic ice gets in the wintertime. It's actually started to break up a lot more than in this image. It's an old image from 2012, which is about the time frame that the test was probably put in, so we're not too far behind the test here. But if you look at these graphs, here this is showing the sea ice extent over a period of 30 years. Here we're looking at extent the same time frame, but we're looking at the volume of the sea ice. So what we're seeing here in the first graph is every year the amount of coverage of the ocean is declining. It's getting less and less. And then in the second graph, we're seeing that the thickness of that ice is getting less and less. So our negative feedback here is the ice and snow works kind of like a mirror, reflecting sunlight energy back out into space. Remember, we talked a long time ago, the first of the year or something like that, that light energy comes in, it bounces back out into space, a lot, some of it. Snow, a lot of it, like 90% of the light bounces off snow and comes right back into the sky. But when it becomes absorbed, that's when it turns to heat energy. So the snow reflects more than it absorbs. It absorbs a little, but it reflects more. So when it melts, we have a really transparent fluid here called water on the planet that absorbs that light radiation. And when it absorbs the light radiation, it will turn it to heat. And so if we melt more and more of this ice in the Arctic Ocean is going to have rapid warming, and it's going to cause for more melting of that sea ice, more melting of the sea ice causing more warming, causing a positive feedback loop. Now, how we know about this climate? How do we know we're even warming? That was the job of the IPCC. I say that slowly because you need to know that. IPCC stands for Intergovernmental, said that a little fast, Intergovernmental Panel on Climate Change. And I swear I had one of these. I don't have it open anymore. I'll open it in just a minute. Okay, here's their website. I couldn't find a quick good image. Anyway, so IPCC, it's right up here in the right hand corner. Now what their job was, they were formed like 70 years ago, way before any of us were born, but their job was to find out about past climate. How has climate been throughout Earth's history? And then their second job was to discover if we were having climate change. Now they were created because we started noticing changes in the arrival of spring. We were noticing that the blossoms were starting to come out earlier and earlier every year. And we were starting to notice changes in our planet. We thought, okay, maybe the world fluctuates a lot. Maybe we don't know if we're affecting the climate. Maybe this is just a natural phenomenon. So what their job was, what they discovered was that, yes, we're definitely warming the planet. Yes, it's definitely happening now, and consequences of that are occurring all around the world. And it's not a natural phenomenon. It's not something, not connected to one of these natural cycles that we have in the planet that's causing us to warm, because most of those are suggesting that we should be cooling. So what they discovered, that it was from human processes. Two things. It's caused by fossil fuel burning, and it's caused by deforestation. So not only are we burning and putting more of this organic material, burning it directly into the air, but we're burning our forests, and we're cutting down the forests that actually do that carbon sequestration for free. It's absorbing carbon out of the air all the time and storing it in the biosphere. And we're like, oh, let's cut that down. It's not the smartest of strategies, personally. So the IPCC, Intergovernmental Panel on Climate Change, know it, remember their purpose. Okay, I forgot to mention one of their purposes, and that is to project future climate change. And I also didn't tell you who it was made up of. So they didn't just make it up of scientists here in the United States. They didn't just make it up of just random people wherever. They made it up from many different nations around the world. And it consists of more than 2,500 climate scientists from around the entire planet. So these people have a pretty good handle on climate and what's going on with that. Now, how do we actually know we're warming? Some of our main evidence comes from ice cores. You might see stuff about ice cores on the examination. Basically, the ice as it forms has little air bubbles trapped inside of it. Those air bubbles are a capture of the they're a capture of the air, the atmosphere at the time that ice was frozen. So this is what the ice core looks like. It looks like a cylinder because we cut it out of the ground with a hole saw, basically, a very long hole saw. You can kind of see that image represented here. But these ice cores, and here you can see a very dark band here. This, I would guess, is either a prolonged volcanic eruption, or this might be soot from when we started burning fossil fuels in the early Industrial Revolution, where we were putting out a lot and we weren't really protecting people by, filtering that stuff we were burning. So a lot of soot was just going straight into the air and painting everything black. But here's a close-up look of what this examination looks like. These little tiny specks in here, these are air bubbles, and we've got dusty layers, we've got air bubble layers. This is kind of like a tree ring, where you can see the different layers in the ice represent different years. And we can go back here, the ice cores on Greenland ice sheet, I think. I'm not sure on this one, but one of the ice sheets, either Antarctica or Greenland ice sheet, goes back 800,000 years. So we can see 800,000 years into the past with these. We also have things like tree rings. I don't think you need to know any of these things of how we figure out climate change. The book pretty much says, okay, we know it's real and we're focusing on how it's affecting human populations and the world populations. But we not only have these ice cores, but we also have other things like tree rings. Trees will grow based on the climate of that year, and every year it shows you that ring, and you can kind of tell some information about that. We also, we also have stuff, sedimentary rocks that also do this kind of thing where they grow in layers and layers, and they trap little air bubbles inside of them. These are specifically stalactites and stalagmites do this as well, and we can slice those open and take some data from that. But there's a lot of different ways that we can tell about Earth's past climates, which I don't think you need to know, so we're going to go ahead and move on. Okay, so the Kyoto Protocol. Let me get it up on the screen real quick so you know what I'm talking about. It is KYOTO Protocol. I don't know what I'm going to get. I'm just going to search it up here. So basically, the international agreement, we have two agreements that we need to know. Kyoto Protocol is one of those. Basically, it commits parties to meet certain restrictions, and it's trying to combat climate change. So both of our things here will be combating climate change. However, there's a lot of nations that are signed up with this, but a lot are withdrawing because it seems like the limits that are set on their carbon emissions that they can put out are a little too stringent. So the 2020 and the 2050 goals that basically it's set are too much for the countries to meet, and so a lot of countries are pulling out of this. However, we have another one that is the Paris, you could call it the Paris Agreement, the Paris Accord, the Paris Climate Accord, and if you recall, we just withdrew from that as a nation because that's something we did. Yep. But that won't be on the exam because that happened this year, and nothing that happened this year will be on the exam. So, anyway, so pretty much every nation except for 2 nations, according to the exam, 3 now, yay, have decided to go to this agreement. Basically, countries set their own targets on what they meet. There's really not any consequences for not meeting your targets, but countries kind of pay in money to but also help this, and they say, okay, we're going to restrict our carbon emissions, or we're going to restrict our nitrous oxide emissions, or we're going to restrict our methane emissions, and they work to basically better the planet. Let me see if I'm missing anything here that we should have. Government aims to respond to global climate change threat by keeping global temperature rise this century, this is important, well below 2-degree mark. So we already have about a degree of warming coming up really close now, and we're trying to stay below that 2-degree warming mark because we think that actually might be a point of no return kind of a location. So we're trying to keep us from having 2-degree of warming, and we're trying to get back to in pre-industrial revolution levels. We'll see. Next thing here, possible effects of climate change. So, no brainer, habitat loss. That's duh. We know that. Melting of the permafrost is one here. Permafrost, remember, permanently frozen ground. Got a lot of organic material in it. If it starts to decay, it's gonna eke methane into the atmosphere. Methane is a stronger greenhouse gas. I don't know where I'm at. Okay, so this is kind of an image. Boreal forest. Now, forests, this is probably going to be on the examination, talking about forest, boreal forest, northern forest, sort of receding up to either higher latitudes or higher altitudes. For a few reasons for that. Trees are not uprooting and walking up the mountain. That's not a thing trees do. They don't walk. So what's happening is basically the higher elevations that were not suitable climate, or the higher latitudes where they're not a suitable climate, are now starting to thaw out. The seedlings are now being able to take root, and the forests are starting to expand. Now, lower down on the planet, it's starting to be inhospitable. The climate's altered. It's not going to be very productive. And so we're actually seeing a lot of our forests in the United States, they're receding higher and higher, going up higher into Canada because it's becoming more suitable way up higher, where we had the taiga forest. Taiga is not a forest. Everybody knows that. The taiga, and then the boreal forest is kind of creeping up into that taiga, while down below where we have those forests, they're sort of receding because it's becoming too warm to support them. Warmer temperatures, more evaporation, and we can't support forests. Remember, trees take a certain amount of precipitation. Another consequence is ocean acidification. I think that's in here somewhere. Oh, sea level rise. We'll start with that because that's higher. Sea level rise. There's a lot of nations that are at sea level, slightly above sea level. Miami is an example of this. A lot of parts of Louisiana. We're already losing a lot of the Everglades. What's that country in the Spain country? Whatever. There's a city, and I forget what it is right now, where they're being inundated with too much water, but they were already sinking to begin with. But we have a lot of this water inundating our shores. Miami's going to be underwater soon. They're paying a lot of money to raise the streets to try to pump water out during the king tides, which is basically during high tide, where the ocean water is the highest. King tide is a time where the moon is sort of closer to where Florida is, so the high tides are extremely high. We've got flooding already happening in Florida. So we're already seeing these effects of climate change. There are already nations where houses are being washed away on their island nations because the sea level is rising. Sea level rise is going to be due to partly because the ice is melting. Water's going into the ocean. The biggest part of sea level rise, however, is the fact that we're warming up the ocean. And the ocean's a lot of stuff. And when you heat something up, thermal expansion makes it expand, and it's going to take up more space. So same water molecules, just literally taking up more space, causing flooding because or outgrowing its container, I guess I should say. Not only are we having flooding from the ocean because it's outgrowing its container due to thermal expansion and from melting of the ice, but then we're also going to have an increase of drought. So basically we're having more severe weather where we're going to have a yearly amount of rainfall that are going to fall in like a small amount of time and causing severe floods. And then other times we're going to have drought and we're going to have shifting of the weather. Oceans are becoming more acidic. We have ocean acidification. Now, our lab that we did this year was one of the, labs that you're supposed to do for environmental science, but it's not a very good show of it because really the ocean's not becoming acid, it's becoming more acidic, or it's actually becoming more neutral if you want to put it that way, but we call it ocean acidification. Now remember, that happens because carbon dioxide in the air mixes with rainwater and it causes it to turn into carbonic acid. It's H2CO3. Yes, because it's carbon. Anyway, that rains down into the ocean. And what that does is it is causing the ocean to be more acidic. So should be at about 8.5, I think, on the pH scale for the ocean. And we're dropping down to something more like 8.2, 8.3. What's actually happening that's bad for these shelled organisms like coral and snails and clams and everything, all mollusks, well, not all mollusks that have shells, is the carbonic acid reacts with carbonate ions. Carbonate ions is what organisms take into their bodies to make their shells. Now, their shells aren't like rocks. They don't just stay there. They're living cells, like your bones are living cells, and they break down and they have to be repaired and replaced. When there's fewer amounts of this carbonate ion inside the ocean, because it keeps reacting with the carbonic acid, then there's less of that stuff around. So it'd be like you not having as much access to calcium. So maybe your food source that you have, you don't drink any milk, or you're not having that lovely stuff called kale. You're not eating the things that you need to absorb calcium. Your bones are going to get weaker because they need to be maintained. And so this is what actually the problem with ocean acidification, that we're not being able to maintain our shells. Now, another thing that it should be in here, but we talked about this before, but it also is leading to coral bleaching, where the algae are sort of dying in these corals. The algae are the ones that bring the coral food, or get the coral food through photosynthesis, and they're not able to, they're basically starving to death. That's what coral bleaching is, and they go white because the algae is what makes them colorful. Anyway, some more severe weather. We're going to have more energy in the atmosphere because we have more temperature, and so we're going to see higher hurricane scales. So like we saw a few 5s this year, we saw a few 3s, few 4s. When we're typically used to seeing 1s, 2s, and 3s, we're seeing more intense storms coming. Now, this year was actually technically a La Nina year, so we did see a high increase in hurricanes because of that. But the intensity level doesn't necessarily go up during a La Nina year. Extreme weather, we already talked about that. Unrest. This is not on this page, so just ignore that. War. When you have a strain on resources, we have war on the planet. That's just the way things go. We're seeing war in Syria that's been stressed through climate change, through restriction of water. We've seen wars throughout the Middle East. So we've got issues with a lot of this stuff that we're kind of not seeing the consequences, or didn't know the consequences of. Climate disruption is a threat to biodiversity. Okay, that's kind of a no-brainer. Climate's changing. It's going to threaten biodiversity. Example of that is the cloud forests, like in South America, or anywhere actually. You raise the temperature, the cloud forests, they're not actually cloud forests, they're actually foggy all the time, and so they don't get direct sunlight. Sun comes through, evaporates the fog, and you get direct sunlight. Evaporates the vernal pools, and we actually have an organism, the golden toad, went extinct very recently after we had discovered it. Mainly because climate change was enough to cause full sunlight on this forest, and it altered the climate pretty drastically. Another thing here, malaria. Let's talk about malaria. Hi, mosquito. All right, so things that are waterborne diseases, they're going to happen more often. Fungi are going to happen more often. West Nile virus is going to happen more often, and at higher latitudes, because these mosquitoes, well, this specifically, West Nile and malaria, they can survive at higher and higher latitudes now because it's becoming warmer and warmer at other latitudes. So they can survive through the less harsh weather, basically. That's what it is. So I'm getting distracted because I have to talk about worms and parasites. I don't like those. So basically, here's a mosquito. She's getting her belly full of nice red blood. Well, some of these mosquitoes have malaria in them. It's a parasite. It lives, a worm, inside the belly. And when she bites you with her proboscis, well, not really bite, but she's sucking your blood with her proboscis, the malaria crawls in, causes cramps, diarrhea, vomiting, fevers, and death. And a lot of people, especially young people, young children, die of this. This is one of our major killers in the world. Let me look at my cheat sheet. Where was I at? Ocean acidification, severe drought, severe weather more common, food production. So this is agriculture. It's going to affect our agriculture. Unpredictable climate, obviously more rains, less rain, going to make it hard to grow stuff. Bark beetle, did not talk about that. So let's look up the bark beetle. All right, so bark beetle, You've probably seen effects of the bark beetle when you've been out hiking. Let's see these patterns. You see these patterns in the wood here, in a dead tree that's fell on the ground. So we've got these places where the bark beetle larvae have eaten inside the bark. This is the living part of this is kind of a bad photo here. But usually these beetles stay in check due to climate freezing. The forest gets cold and it kills most of the beetles off. And some of the beetles survive. They harm the tree a little bit, not really a big deal. Tree survives from year to year and maybe shortens its life, but it's okay. Now, problem with the climate, as it's getting warmer, the winter frost is not basically killing them off. So bark. Sorry. So let's just get some pictures of these bark beetles. So here's some examples of forests that are dying due to this bark beetle. That's a sad forest. So this is not a forest fire. These patches are really old dead. These ones are newly dead. And here's some trees that are trying to survive due to this bark beetle infestation. Basically, the winter frost isn't killing them off, and they're just going wild. Let me look at here. My cheat sheet again. White nose syndrome. This is an example of fungus. Fungus, warmer, moister climate definitely favors fungi. Here is some example of white nose syndrome. They call it white nose syndrome because it's a fungus that grows on them that kind of turns the bats white, especially their noses. It does harm a lot of their populations. A lot of deaths have occurred from this white nose syndrome. It affects their immune system and kills them off. Not all of them, but some of them. And so it's affected bat populations quite a bit. And that's been attributed to climate change as well because it's warmer, moister climate. Mold loves warm, moist situations. As far as human health is concerned, molds and fungus are going to lead to more asthma attacks, also lead to a lot more allergies. Now, possible tipping points. So it's possible. So basically, a tipping point means the point of no return. Point where we've gone so far that the new normal has now taken hold and we're not getting things back to the way they were. One of those tipping points is raising the carbon dioxide levels in the air to 450 parts per million. Right now, it's about 408. So if we raise it to 450, that may be a point we can't return from. Now remember, we're going about 2 to 3 points per million every single year as we tick up. If we melt all the ice on the planet, definitely point of no return. Severe ocean acidification. If we have severe ocean acidification, we could kill off the phytoplankton. Phytoplankton, remember, is kind of like plants. Just think of it as plants. Most people call them plants. They're not really plants. They're protists, but it's okay. They're photosynthetic organisms that live in that photozone, that light zone of the ocean, light zone of lakes, and they're the base of the food chain for every single organism in the ocean. All of them. And they also produce 54% of our oxygen, so it's pretty stupid to be screwing with them. So yeah, don't mess with the phytoplankton. Another turning point would be, tipping point would be massive release of methane from the Arctic from melting that permafrost. Some scientists believe that if the Western Antarctic ice sheet melts, then we're probably problem. And then severe shrinkage or collapse of the Amazon rainforest. The Amazon rainforest subtracts a ton of carbon out of the atmosphere. I think some estimates put it almost at a third of the carbon that we put in the atmosphere is sucked out by the Amazon rainforest. That's a third. The third is responsible to the oceans. It's something big. We need to not kill the Amazon rainforest. It's bad. So things we could stop doing is we could stop burning fossil fuels. That would be the first thing to do, and start using wind farms and other stuff. Mitigation. That basically means means to fix things. How are we going to fix it? So how are we going to mitigate things? Electric cars, no-brainer. Start using electric cars, even if it's from a coal-burning source it's getting electricity from. Coal-burning sources are because of the filters we put on the factories, it's actually cleaner than it would be just to drive our cars around. But also using wind farms, using alternative forms of energy. That's like pretty much a no-brainer. Control or prevent greenhouse gas emissions. There's also suggestion to improve efficiency on cars and on what we do use for fossil fuels, but just don't use fossil fuels. And then carbon sequestration. We talked about this before. Removing carbon dioxide from the air. Few ways we could have GMO trees where they actually grow faster, so they're sucking up more carbon dioxide in a shorter time span. And other ideas are to take ocean water, spray it in the air. We've got the salt particles where more clouds can form on it. And then we've got more cloud formation. Clouds are white, they reflect more sunlight. They also help cool because of that. And then if we could get more precipitation from them as well, it'll wash out some of that carbon dioxide in the rain into the oceans. But then again, we're going to be adding more carbonic acid to the oceans if we were to do that. Another one is and I think I have this on our textbook, but another idea is to put out satellites that are basically like massive giant mirrors out into space that would reflect sunlight to stop it from actually reaching our planet. There it is, right there. Orbiting satellite space shield, where basically we just put these up so it just reduces. It just seems ridiculous. Just stop using fossil fuels. Another way is to put aerosols into the atmosphere. Aerosols that help reflect sunlight and basically just shade it in tiny little particles. So the same idea kind of as the orbiting satellites, but in tiny little particles. A few ways we thought about doing this is using high altitude balloons and then dispersing them with the high altitude balloons. Any kind of passenger jet planes, we could equip them with this stuff as well that allows it to put it out. Let me see if there's anything else I forgot. All right, I think that's it. Read chapter 19. Seriously, read the chapter. I know you guys don't read, but this chapter is really going to help you understand climate change really well, and climate change is 10% of the exam, so read it. Also read your prep book over the weekend. Countdown started. After today, we have 6 days remaining. That's all you have to study, and I know some of you haven't started yet, so start studying because you already paid for the exam. No pressure, no stress. Okay, bye.